Hello everybody and welcome to the next lecture on verification. So, if you recall, we are in the double lecture series on symbolic model checking. So, just quickly recollecting what we were discussing is that if we had look at the model based verification, so we already found that it is actually the modeling of the system which is actually taking a lot of complexity, and on that if you want to model check any of the CTL or the LTL formulas, then what we are being killed about in the exponential complexity is the size of the model. So, what after that basically we have seen that BDD, which is one of the very key role playing mechanism to help us to alleviate the complexity problem, to eliminate the complexity problem, is the BDD. That with the BDD or symbolic mechanism we can handle the complexity up to a large extent, because if you are using symbolic modeling and verification, we are not exactly modeling the system in terms of explicit state space. Rather, we are modeling the system in terms of binary addition diagrams, and then we are using those binary addition diagrams itself to model check the formulas. Because we have already seen that model checking means just the labeling algorithms which we have a linear, or you can think about non-exponential complexity. The exponential complexity is basically incurred in the size of the model. So, what here we are doing in symbolic model checking, we were representing the system itself in terms of BDDs rather than the explicit state based enumeration. Then all the labeling algorithms we were doing in the symbolic model checking. So, in the first lecture basically we quickly covered, that is lecture number 4, we quickly covered about how BDDs can be used to represent sequential circuits, basically the states, and then we have seen basically quickly how transitions can be represented, and then basically there is some kind of ROBDD which represents the states, substates of states and the transition relation. Then what we had seen, then basically we had gone to the symbolic model checking, in which case we have given you an idea, rather by taking a cryptic structure, then this model basically we represented in terms of basically the BDDs, and then we have shown elaborately in the last class that how symbolic model checking can be done using such a cryptic structure which are symbolic, and we have very elaborately seen two formulas, temporal formulas, that is EX, that is there exists a path in next state some formula should hold by using this model checking algorithm, and also we had seen basically another one, that is the AX, that is from a given state in all paths in future the formula should hold. So, basically till now we have seen EX and AX, the two formulas how we can do a model checking, that was covered in the last lecture, this is lecture number 4. Now, as we know, they are basically, we have also shown that given any model, any cryptic structure, we do not explicitly model them in terms of states, rather we model them in terms of BDDs, and then we have seen how the labeling algorithm can be done symbolically itself in those BDDs. Using this we can do labeling symbolically on the BDD itself rather than on the state space, rather than the state based cryptic structure, and as an example we have seen two formulas, that is EX and AX. Now, basically we are going to see, we already know that EX, AF, that is the first lecture, and EU. So, in the first lecture if you recollect on verification, we told you that basically there are three basic formulas, EX, AF and EU. So, within these three formulas basically all the other CTL formulas can be modeled, or you can write other CTL formulas in terms of these formulas, and so therefore we can call them as the basic or building blocks, or you can say that if we know symbolically how to model check for these formulas, then any complex formula can also be written and model checked using symbolic model checking. So, EX already we have discussed last day. EX means just if we see basically EX is nothing but what we mean to check is that from any state, say this one, in the next state, that is because of X, some formula should hold. Basically this is nothing but your existential quantifier, that is if you look at last time we have done this one, so we generally call it as existential quantifier, this one. So, pre of X. So, pre of X is nothing but from any state X, means what, maybe there may be some states in terms of X, from where basically there exists a path where this is the state, some state X where the formula intended to be true, and means there should be a state from which there should be at least one path leading to a state in the next. So, this may be a path, and there should be at least one path to a state X where this formula in X should hold. Then we can label it as existential of X. So, this is nothing but you can call it as E of X. of some formula x. Now, why is it? Because from this state there exists at least one path to a next state where the formula corresponding to this capital X holds basically. So, that is the idea. So, Ex means what I mean to say is that Ex means basically directly we can have basically that their existential pre of existential x is directly mapped to the formula of Ex. That is all states from which there is a path, and in the next edge basically, you should not call it the path, it is basically the edge. So, from a state like this, the edge and the state, here the property basically which is required to be true has to hold, there should be existing a path. So, that is Ex, and basically the formula that is pre their existential x actually caters to that. Now, as I told you, that is what we are going to do today, basically that three formulas are building formulas Ex, Af and Eu. So, Ex we can directly say that is pre-existential, actually caters to this, and now in this today's lecture we will elaborately discuss on how we can go for model checking for formulas Af and Eu using symbolic model checking. So, and for this we will be very elaborately using these two functions, two things already we have seen, that is one is pre of x and one is for all existential pre, that means from this state there exists at least a path where x is holds, and in case of for all, that is pre for all clause, then for all paths from this state your property of x, whatever property you want to satisfy in x should basically hold. So, and we already have discussed in lecture 4, that is last lecture, elaborately how we can model check for this pre all and pre x. Now, because as already I told you, pre x is directly related to Ex, so we drop the detailed lecture on this, because Ex means directly you can apply pre of x existential x and your job will be done. But the two other formulas, that is Af and Eu, requires elaborate discussion that how can we model check on them. So, let us start with Af. So, what is basically Af? Means there should be a state say, and then all paths from either state in future some property x should hold, then only we can say that Af of x is true. That is, for example, it is saying that Af b of phi. So, it is saying that this says that in future this some phi formula is true in some states, then only we can say that Af b of phi or phi actually is satisfied by this state. That means from one state, if you take all paths or if you take any path, and in future in a state the formula phi basically holds true, that is actually Af formula mean. Now, how to go for a symbolic model checking using this one. So, this is the algorithm. So, b of b, this b with an arrow sign basically is the BDD representing the transition relations. Already we have seen in the last lecture in elaboration that how basically BDD can be used to represent the all transitions of a state machine or the Bookie automata in this case, sorry, the crypto structure in this case. And then b of x is the OBDD for all states of the system. So, initially you say that you just have a BDD which represents all the states of the system, or just an initialization. Then what we do, we repeat till b of x is equal to b of phi. So, b of phi basically is the OBDD of states where the formula phi is equal to 2. That is very important for us. Bx is some arbitrary initialization. So, initially what they have done, they have taken all the states of the system and they have made basically a BDD for that. So, initially what we do, we will repeat till b of x equal to b of phi. So, as of now basically bx can of course, if it happens that this phi is true everywhere. So, in a very stray case it may happen that there are 3 states in the system, or say for example, okay, and everywhere the phi is equal to true. Then we should not do anything, actually we can stop the algorithm there itself, because in all states your property is true. So, in all from all states, from all paths in future phi is true. So, of course, if in this state phi is true, in this state phi is true, and in this state also phi is true. So, of course, from that state all paths basically in future phi will be equal to 2, because present is also considered as future. So, that is actually vacuously true kind of a thing, that without even starting from that state your formula is holding true at that state itself. And if it holds for all the states of the crypto structure or your system model, then of course you need not do anything, you can stop there itself. So, what we do initially, b of x you assign all the states of the system and then you repeat until b of x equal to 2. That means, if it happens that in all the defect case that all the states have the formula 2, you stop there itself. Else what you do, you assign bx equal to b of phi. Now in this state basically your Bx will now not have all the states of the system, now it will have only the states of the system where phi is true. Here actually it is now B have become a temporary buffer. What it is doing, wherever states actually phi is true, that now Bx is holding as a temporary buffer. Now B phi will be updated. So what we are now having, Bx is now holding all the states phi where at the present iteration phi is equal to true. So now B is a temporary buffer. Next we will update B of phi. So how do you update? If you recall, in the first lecture we have shown how AF is labelized. So what we do basically, we say that any state here where phi is true, basically you have to mark as AF phi, right. So any state where phi is true is AF phi is true, because present is future. So in that state phi is true. So of course in all paths from the state phi is in future is going to be true, because this is the state where phi is true. So any path if you take, obviously phi is going to be true in future because present in future. That is, before starting itself your formula is satisfied. So you have to mark it. Next what you do? Next basically now this is done, then you have to see this formula or this way of calculating symbolically, because pre of all, that is pre existential and pre for all. So these are the two basic structures which will be used for symbolic model checking. So already we have discussed in the last lecture how pre of existential and pre of all is calculated. So what it is saying, pre of all B phi. So what it means, that means there may be say some 3 or 4 states in which case say this is phi is true, this is phi is true, and this is where phi is true, and there is one state where these have only 3 edges, no other edges is available. So from this state basically you know that all the paths lead to states where phi is equal to true. So you can say that here basically this formula is satisfying over here. So now what it is saying, this for now you say that you take all states where B phi is true like this. So in these states basically obviously your AF phi is equal to true, because phi is true in that state. Now you take all such states also. So all these states will be there. You take all by this formula it is saying and apply. You can see B of phi pre is something like this, where basically this state is such like there is one edge from each from this condition there are 3 edges, for example all the possible edges, no more edge exists, and in that edge phi is equal to true. So here also B of phi, that means A of phi has to be true, and then you say that you take states like all states where A of phi is equal to true, sorry, you take all states where phi is equal to true, and all such cases like this where basically in the next state phi is equal to true for all edges, and you take this union of this and union of this, and you are going to apply this one. That means this one actually what it is doing, it is taking all such states where phi is equal to true, and this is pre of all B phi is taking states of this nature, and you OR them. Basically these are the states in which AF phi holds, and you have to keep on doing it till you are not going to get any more states. Then basically what you are getting AF of phi. So that is a very simple idea. That is, first you label all the states where phi is true, that is where AF true is true, as well as you have to also consider this one in iteration, that is take a state where all the next states phi is true for all the edges, that you also mark as AF phi, take OR of this, and this is one iteration done. You keep on doing it, and then whenever your algorithm will stabilize, you are going to get basically AF of phi, and you have to do it symbolically. Of course this can be done symbolically, because if you see already we know that this one can be done symbolically, already we have discussed, and applies the OR operation. OR operation can also be done using a BDD. So this is the symbolic model checking algorithm for A of F. Just recollecting what I have told using a diagram. So what is AF of P or phi in our case? So if any state S is labeled with P, label it with AFP. That is true, as I already told you, and then you have to repeat it in a loop, label any state with AFP if all its successor states are labeled with AP until there is no change. So whatever I told you diagrammatically is written in this slide. That is, AFP's formula is P, either P is true in that state, or in all states from X, that is all states in future, in all states in, that is AX AF means for all states there exists a path such that in all states in future P is equal to true. That is, this one corresponds to the case, the states where phi is true, and this part of the formula corresponds to the fact of this one. That is, there is a state from which in all paths in future phi is going to be true in the next state, that is this one, correct. So, as I told you, this one already we have discussed in the initial lecture, so you can just recollect it. So, this is the formula and just pictorially representing. So, these are the states in which P is equal to true. So, of course, you have to mark them AFP, AFP and AFP. By default, they are going to be marked, and then basically as this all these states are such that P this one is equal to true over here, you also make it as AFP. So, that is one way of or the way of actually labelizing the states for AFP. So, this already I have shown you this pictorial diagram, basically already we have shown you in this first lecture, but I am just repeating you so that you can get a recollect the lecture. But this is not symbolic. So, this part actually is a state based representation, but now we are going to do it symbolically. So, this one was a symbolic manner, that is using BDDs, ORing them, pre-calculation, that is a symbolic way of doing it. But this example I have told you is a non-symbolic way of doing it, but just to correlate the fact I have shown these two slides. But now again let us come back to our real business, which is on AF, and we are going to do in a symbolic manner. So, this is an example of a cryptic structure. I am zooming it for you. You have to always keep this structure in mind, because throughout today's lecture we are going to use this example heavily. So, there are three states in this cryptic structure, okay, and then here x1 is false, x2 is false, s1 x1 is true, x2 is false, and in s2 both x1 and x2 are true, correct. So, now symbolically, as I have already discussed in details, I am not going to again revise that again, because last class we have done. So, this one is the BDD corresponding to the state S0, this one is the BDD corresponding to S1, and this one is the BDD corresponding to S2. You can easily find it out, like just x1 x2 means both are true, so then only it will be true. So, if both of them are true, that is why I am getting the answer as 1. If any one of them is a false, the answer is a 0, that represents the state S0. Similarly, all others can be easily explained. Last class we have done this elaborately. Similarly, S1 S2 is the BDD for this, the set BDD S1 S2 for is the BDD for this, and all these states if you take together S1 S2 and S3, this is the BDD. All other combinations can be drawn, but I have not done it here, because basically for the example we are going to consider in this case, these combinations will suffice. And this is the transition relation. So, transition relation also we have found out how to deal with, so that we also put some primed states, like that are the next states. So, these are the next states if you can see. So, along with the normal states we also have the prime states, and we can easily model the transition relations of a cryptic structure or in that manner any state machine in a symbolic manner or using a BDD. So, that also we have discussed in the last class. Now, for this example we are considering, so this is the set of BDDs for states, and this is the BDD for the transition relation. Now, you can easily hand draw them again and to see if whatever we are telling is correct, and that also will give you a confidence of drawing the BDDs for given different state diagrams. Now, coming to real business. Say for example, we are going to verify all paths in future B of phi. So, what is phi of phi here? This is basically your variable called x1. We are saying all paths in future. Let us again go back to the structure, which will be easy for us. Just a minute. What we are going to say? All paths in future x1 is going to be true. That is what we are going to verify by labeling. That is from the states, but from all paths in future x1 should be equal to true. So, if you can see over here, before doing it symbolically, let us take a layman's approach to see what is going to be the output. So, if you look at this state, if you look at this structure, it is very obvious that from all states this formula is going to hold. The formula is all paths in future from a state, all paths in future x1 is going to be true. You can see from state x1, if you see, this is a path, x1 is going to be true. This is a path, again x1 is going to be true. So, from S0 all the paths in future will give you x1 true. If you take S2, so there is one path here, this path is this, and this is a two hop path where x1 is going to be true. That is for S1, and there is only one path from S1 outgoing from S1. So, if you take S2, S0 and S1, x1 is going to be true. So, S2 will also satisfy the formula, and S1 state itself x1 is going to be true. So, we can see that in all paths in future, so from S1 x1 is true, so by default it is true. From S2, if you see here also x1 is equal to 2, default it holds, and also you can see that this one is also, if you take this path also x1 is going to be true in future, any one you can take. And from S0 in the present state x1 is not equal to true, but we require in all path in future x1 is going to be true. So, if you can see this is one path where x1 is going to be true, there is one path where x1 is going to be true in the next state. So, of course, by a simple intuition you can find out that in this script structure in all paths in future x1 is going to be true, fine, and in which states x1 is true, that is S1 and S2, that is B of phi, that is x1 is true in the two states, that is S1 and S2, correct. So, now we are going to inherently we have in our mind that all paths in future x1 is satisfied by all the states of that script structure, but let us do it symbolically. So, first what do we require? The first state we require a set of all states, that is B of phi, where the x1 is true. So, already we have shown you that this x1 is true in states S1 and S2. So, you have to first draw the BDD for S1 and S2, because it is x1 and x2, x1 is true in the states S1 and S2. So, this is the BDD for B of phi, that is actually the BDD corresponding to S1 and S2. As you already discussed, you can easily find that this represents the BDD for the state subset S1 and S2. Next what we have seen? Next you have to do the calculation of pre. We are just going by this algorithm. If you look at, we are just going by this algorithm. Stepwise we are going by this algorithm. We have to first calculate the transition is anyway there. B of phi we are calculating, that is the set of all the states where phi is true. Then we are going to finally go for this, apply or B of phi, that is in this case S1 and S2, and we have to go for pre of all B of phi. That is, next we have to find out, that is pre of all B phi. So, in this case S1 and S2, so we have to find out basically some states such that all paths from that states leads to S1 and S2. These are the states called, these are the two states where your x1 is true, that is your phi is true. Now, you have to find out such states from where all paths will lead to either S1 and S2, that is nothing but pre of all B of phi. Now, if you look at state S0, obvious, this path and this path. So, all paths leads to the states where x1 is equal to true. But if you see in the next state, means for all means in the next, not in future, basically next state it is true. So, S1 obvious, S0 obviously satisfies because there are two paths from S0. So, one is leading to S1, one is leading to S2, and in both of them your x1 is basically equal to true. But if you look at S2, okay, so in x2 basically if you see the next state is S0 where phi is equal to false. So, that is not going to satisfy, and similarly for S1 also there is one path going to S0. So, in the next step phi is not equal to true, or phi that is equal to not equal to true. So, pre of B phi is only going to be the state S0. That means from state S0 all the transitions if you take, they are going to lead to states, next states from S0 where x1 is equal to true. So, basically, so that is equal to, that is going to be the answer for pre of B of phi. But if you recollect, P of all B phi, we actually do not go in a direct manner, we go for in an indirect manner. First we go for B of S minus phi. That is the set of all states where x1 is not equal to true, that is equal to the S0. So, last lecture if you recollect, we have where we are showing the algorithm, where we have showed the algorithm for pre of all, we do not directly hand calculate as we have seen from the on the crypto structure, rather we are taking a negated way of doing it. First we find out all the states where phi is equal to false, and then we will try to find out all the states from where there is at least one transition to the states where phi is false, and then we will subtract it from the state space, entire state space, to get the answer. So, anyway, going by steps. So, B of S minus phi, that is the set of all states where x1 is not true, that is equal to nothing but S0. So, this is the BD for S0. Now, we are going to find out the set of states. So, we are having a states called S0, right, that is the last one, S0, where your formula is false. Now, you have to find out any state where there exists at least one path to S0. So, if there is at least one path to S0, that means all paths from these states, these two states are not leading to states where x1 is equal to true. So, that we are going to, so that will not be considered. So, that is we are going to take in a negative way. So, if at least there are two states, for example, which have at least one path to S0, so they have to be negated from the answer. So, if you calculate, if you look at the crypto structure here, so and what we will see that basically S0 is the state where it is false. So, if you just look at here, so S0 is the state where x1 is equal to false. Now, all states which have at least one transition to S0 will actually not satisfy the, has to be computed now. So, from S1 you can see there is at least one path to S0, and from S2 also there is at least one path to S0. So, what does it mean? Basically, if you compute, there exists a path, this one is basically not but S0. So, what it is saying, pre of S0 means there will be two states S1 and S2. Now, what that indirectly mean? That indirectly mean that, so this is the B0, this is the BDD for S1 and S2, because S1 and S2 are the two states from which there is at least one transition which leads to S0, and S0 is this case where your formula phi is equal to false. So, now what you are going to do? Now, we are simply going to say S minus pre of B S minus phi. That means, this is the state, these are the states S1 and S2. So, these are the two states S1 and S2 means there is a path from this S1 and S2 which leads to state S0 where your formula phi is false. That means, obviously, these two states cannot satisfy the formula of all paths pre for all of your phi, that is x1, because there will be at least one transition, in this case to S0 where it is false. So, these two states will be not satisfying your clause of for all phi pre for all phi x1. So, this will be eliminated. So, now basically what we do, we will now subtract this S1 and S2 basically from S0, and you are going to get the solution answer as S0. So, basically pre of all B phi, that is equal to pre all B phi, that is equal to x1, we are going to only have the state that is actually S0. So, now intuitively what we have done, first we have taken the set of states where this is false. So, x1 is false. So, that is nothing but your S0, that is the S0, that is equal to this. Next, what you are trying to do? Next, you try to find out all the states like this one which have at least one transition to the states where B1 is false. So, in this case S1 and S2 will be there because there is one edge to S0. That directly implies that for all existence, that is for all pre, cannot be satisfied at S1 and S2 because they are having at least one transition to a state where the value is false. So, if you subtract S1 and S2 from the entire state space, here we are getting the value S0, a state S0, that is actually satisfy the case, that is the state from where the next state phi is equal to true. That is, in this state the property which holds true is basically for all true, basically that is from this state. If you take transition, all transitions from this state, they lead to transitions, they lead to states where x1 is going to be true. So, pre for all x1 is basically satisfied only in the state S0. So, this is how we actually symbolically calculate the value of pre for all x1, that is B phi. So, that is actually, now we are in the case where we have got symbolically the value S0, that is this BDD, which corresponds to pre of all B phi, that is equal to x1. So, now what we have at hand? So, now we have at hand the symbolic representation for this set of states such that in the next state, that is some states like this, where in the next state your formula x1 or your property x1 is true. So, this in this example is x0, but in the general case you will have a set of subsets of states which will be represented by basically your binary decision diagram, that will be done symbolically. So, now we have a set of states like this, where in the next state this property is true in all the paths. So, you can very easily say that all paths in future phi is definitely going to be true over here, in this case x1, because next is also a future. So, this one will be basically labeled. Now, we have to also label the states where x1 is true by default itself, like in state S1 and S2, x1 is true, here also x1 is true. So, in these states obviously AF x1 is true, here also AF x1 is true. Now, why it is true? Because present is also future. So, in this state x1 is true itself. So, obviously, even if I start from this path, in all paths in future x is going to be true. Okay? So, that is what is the case. So, now what they are going to do is that they are going to take the OR of B of phi with what we have already got. So, OBDD for S0 stands for this, and OBDD S1 and S2 stands for the case, the states where itself x1 is going to be is true. Basically, this is nothing but these two states where they themselves are true at these states. So, you take OBDD of S1, S2, OBDD of S1 and you go for apply operation, applying is all. So, you are going to get the answer S1, S2 and S. So, which we have already shown you intuitively that in the crypto structure for all paths where in future x1 is true is satisfied by all the three states S0, S1 and S2. Also, we are getting the same answer symbolically, that is again This S1 and S2 are coming into this class because x1 is true in this state itself, and the state S0 is coming because all the paths from S0 next state if x1 is true or x1 is true in that part. So, if we make a union of this, we are going to get the answer, which is S1, S2 and S3, sorry, basically S0, S1 and S0, S1 and S2. So, slight typing error. So, all the states will be basically included over here. As all the states are coming as the answer, so no more repetition is required, no more iterations are required, you can stop and your model checking will tell you symbolically that your formula AF x1 is true in all the states. So, again just recollecting again by this algorithm what we have done. This is where is the algorithm. So, again just a quick recap. So, what we had done, basically we represented B of phi as a PDD, and then basically this pre of all we calculated in an indirect manner. That is, first we calculate, we compute phi minus, that is phi negative is false, then we find out existential pre, and then we subtract whatever answer we get, we subtract it from the whole state space and then we get the answer. So, I think in this case we got the answer of S0, and basically, and then what we have done, then B of phi are the states basically where the variable, the formula to be verified is true by explicit itself, explicitly true in the state itself. So, we got S1 and S2. So, these are the two states like S1 and S2 where x1 was true itself, and but for the state S0 which we had found out over here, this is a state in which case in the next state the formula AF phi or AF x1 is true. So, of course, we are also labeling it as AX phi, sorry, AF phi, we are labeling it as x1 here by the virtue of the next states having the value of x1. So, this one is actually computing for this, and then we are going for a OR operation. So, OR means, so this one is going to give you this state, and this B phi is going to give you states S1 and S2, and then finally we are going for an OR operation, and so we are also going to get the value S0, S1 and S2. And basically, why do we end over here? Then the iteration will stop over here because Bx will be equal to B phi. The whole state space will come over itself. And of course, if you would have a very stray case like something like, if you would have something like, just a stray example, if you would have something like in this case, if I again negate the bar. So, anyway I cannot, this will not be holding this example properly. So, if somehow I could have done a case like maybe I would have some x3 I could have over here, and then I would have eliminated this, and I would have also put x3 here, x3 bar over here, and maybe x3 here. I would have just added a variable, and just adding a dummy variable here to just give you the fact that this is this structure in which all the states x1 is going to be true. In such a case, your algorithm basically will stop here itself because Bx will equal to become B phi. So, that is a very stray case, in which case in all the states basically of this system this formula x1 is true. So, in that case the machine will stop, or the algorithm will stop there itself, okay. And also in one more case as it happened here, sorry, if you look at one thing also happened, that after the end that B phi is after you and send the answer by ORing the set of states where phi is equal to true, or in the next state phi is going to be true for all the paths, then basically here we are finding out that all the states have to come into picture like S1, S2 and S3. So, it will again become equal to the set of all states, or in any iteration if you find out that all the state space of the states have been included. So, of course, there is no point in iterating, your answer stops and you are going to get the answer. That is, all the states of the system satisfies the given formula. So, what we have seen? We have seen one very important formula for model checking, that is AF, how it can be handled symbolically. We have given the algorithm, and then we have explicitly analyzed using a very simple example and how it can be done symbolically. So, till now we have learned about Ex, AF. So, Ex, as again I am repeating, Ex is nothing but equal to pre of existential, that is equal to Ex, because it says that from a state there exists at least one path where in the next state it is true, that is nothing but pre of x. Then using pre of x and pre of all, we have shown how can we model AF. So, AF we have learned, Ex we already know from the last class. Then what only more atomic version remains, or I should not call atomic, the basic formula which remains to be explored is EU. With all this you can generate any other CTL formula. So now we will see how to compute EU, that is existential until. Using this, how we can go about modeling any other formula. So we will now concentrate symbolically how to verify EU. So what do we require here? Just similar approach, quickly we can cover this, just same way as we have done for AF. So we have the set Bx is the set of all the states in the system, but there are two formulas because we know that means it is always generally psi until psi 2 or psi until phi. So we have two formulas basically. So this one should hold until this, that is what is the idea. So if you forget, basically your psi 1 should hold until your psi should start holding, that is there should not be any state in between where psi 1 is also false and psi 2 has not true. That means you cannot have any state here where maybe psi 1 is bar is true and psi 2 bar is true, that is in this state both of them are false, you cannot have anything like that, otherwise the formula will be false. Basically psi 1 should keep on holding until psi 2, or in this case psi 2 starts holding, right. So anyway, so there will be one BDD for psi 1, one BDD for psi 2, and this is your transition relation. Now what we have to do basically. So there is the initialization step. So initialization, whatever will be the value of psi 2 formula will be dumped to Bx, that is a temporary storage as we have already done, and you have to repeat till the Bf is equal to psi 2. So of course what did formula say? Sorry, the formula says that psi 1 has to be true until psi 2, correct. So what happens if in the system all the psi 2s are true, then of course the formula is true without any check. So therefore what we do is that basically Bx, basically we dump, basically we repeat this one, basically we check by this formula, we are just going to check that when if Bx is equal to psi of B2, that is Bx is the all the states of the system. So if all the system's states are equal to B of psi 2, we stop there itself. So that is again the similar check like AF. So anyway, and you have to keep on repeating till there is no more changes. Now what we do, how the labelization, that is very very important, that is by this formula. So we will just see an intuition and then we will do it symbolically. So what we do, so it is Ex. So if you look at it is EU, that means there exists a path where psi 1 until psi should hold. So in this case by intuition it should be an AND operation. So AND operation means psi 1 should keep on holding, it should be psi 1 psi 1 psi 1 until your psi 2 should start holding. So what we do, so first is you can see B of psi 2. So if B of psi 2 holds, that means you need not worry at all. So all the states where psi of B of psi 2 holds, you can directly label it. So we are having all the set of states where psi 2 is true, you are including, and we will do a OR operation with this. But this apply, if you look at, so this part basically, this part, this psi 2 and OR, this just simply corresponds to the case where psi 2 is true, because our main job is to wait psi 1 psi 1 psi 1 and psi 2 should start holding. If psi 2 starts holding from any state, that state can be directly taken, because psi 1 psi 1 psi 1 until psi 2. So whenever psi 2 starts holding, your life is safe kind of a business. So basically, so psi 2, we are just keeping all the states where psi 2 will be there, we are going to take it. So that part is simple OR with a psi 2. Now this one is particularly important. So what we are doing over here, in this case we are taking pre of B psi 2, that means there is a state say X, there is some state here. So here your formula psi should hold. So that this pre of B of psi 2 tells that there is a state say X, and this is a state where psi 2 is holding. So this state this state is actually nothing but your pre-existential of psi 2. So this is the state where pre of X holds, pre of psi 2, because this from this there is an H where psi 2 is true. You take all such states and then you AND with a state of B of psi 1. That is what? That is you take this apply means apply dot, that means that this is a ANDing. So what you are ANDing with it? You are ANDing with a state where psi 1 is true, that means you are doing something like this. So again repeating, so pre of this one is going to stand for the states like this, where in the next state psi 2 is true. Along with it, you are not going to return this. Along with this, you have an AND condition, that is apply dot. What is that AND? That in this state psi 1 is going to be hold. So, psi 1 next state psi 2 is going to be true. This is the set of states you are going to labelize, of course, because psi 1 is true and the next state basically psi 2 is going to hold. So, psi 1 until psi 2 very easily is holding in this situation. Such states you will report. Along with that, you will also report some states like this where psi 2 holds itself, like something like this where psi 2 is true. So, that is by the apply and the second part, this diagram as I have explained you corresponds to this, and you have to keep on doing this iteration till there is a fixed point, right. So, again as I told you, again non-symbolic way of doing it, because we have already discussed in lecture number 4, just recollecting. So, what it does, P until Q, how do we do it? Label any state S is labeled with Q, label it with P until Q, because Q is holding true. So, you need not worry at all, life is safe, you apply it, you hold with, you apply labelize with P until Q. Then label any state with P until Q if it is labeled with P, and at least one of its successor is labeled with E of P until Q, that is a safe state. So, what that is your second clause. So, the first clause is very simple, the first clause is add OR of B of psi 2, if Q is there you labelize it, otherwise also you can labelize this one if there is a state like this where P is true and in the next state E of P until psi holds, that is then only you will also label it as P until Q, right. So, that is what is being told by this algorithm which you have already seen in lecture 4 pictorially. So, Q is true over here, so your life is cool. So, here you can write E of P until Q. Now, next state very easily here also basically this is P is holding over here and already you know that P until Q is holding over here. So, here also you can elaborate or you can labelize that E equal to P until Q, whatever I told you is showing in the diagrammatic fashion. So, now you have to keep on doing it, there is no until no change. So, now we will do this symbolically. So, the symbolic formula also we have discussed, it will be collecting a BDD of psi 2, you will be ORing it with this formula which you have already seen, which corresponds to this part, this figure. Again taking an example and finding it out how we are going to do it. So, there will be 2 iteration, one iteration will do it slowly, the other iteration you can just look at this slide and compare and compute yourself. Again the same cryptic structure you are going to take, so we have to keep it in mind. Now, what we are going to say? Here we are going to check EU, there exists a path where psi 1 is equal to x1 and psi 2 is equal to x2. That means, we are going to find there exists a path where x1 until x2, that is what we are going to hold. So, where is x1 is equal to true? x1 is going to be holding true in states s1 and s2, and when state x2 is true, state x2 is true only in state s2. So, that means what? Existential of s1 or s2 until s2. So, that is what is going to be, and there should exist a path where this one should hold. Now, you can see intuitively we can see that look at the state x 0. So, what is the problem with x 0? You can see in this state what it is saying, x1 should hold until x2. In this state you see x1 is also false and x2 is also false. So, of course, s 0 is not going to satisfy the formula. But if you look at this one, x1 is true, x2 is false, fine. But in the next state what is happening? x2 is going to be true and x1 is also holding. In fact, even this prime should not have been a problem. So, what it is saying, x1 is true until x2 starts becoming true. So, in this case x1 is true, x2 false, no problem. Just in the next state you can see, or that is in future maybe, no problem, that x1 is true. I do not bother even if x1 is false here, but x1 is becoming a true over here. So, x1 is holding as long as x2 is not holding. So, s1 is satisfying. In s2 if you see, both x1 and x2 are true over here. So, in whichever state x2 is true, directly we can enumerate it. So, intuitively, and also we will find out towards the end that x0 will not satisfy the formula, but x1 and x2 will satisfy the formula. Okay. So, now again let us coming back to stepwise analysis. So, stepwise what is that? OBDD of psi 1 is s1 s2, this one, OBDD of psi 2 is x2, which is this BDD. Now, we are going for iteration. So, if you look at the formula, so what we have to do? We have to first find out the pre of existential of the states of psi 2. This is the formula. we are going to go by this formula. So, if you look at pre of psi 2, that is equal to the psi 2 means in this case it is x 2. So, where is x 2? So, this one is x 2, this one is x 2. So, okay. So, what are the pre of S 2? So, pre of S 2 is nothing but S 1 and S 0, because that is true, that is obvious. So, basically pre of S 2 is S 0 and S 1. So, what is reflected over here? So, symbolically you can compute the value of pre of S 1, that is BD of S 0 and S 1, that is the states. Psi 2 is x 0, that is state S 2. So, what is the pre of S 2 is S 0 and S 1, because there is a direct edge to this states, and we are going for an existential operation, one path is enough. So, basically S 0 and S 1, this is the B corresponding to this one. Then what we have said, then these are the states basically where there is at least one path where x 0 is becoming equal to true. There is at least one path where x 0 is becoming true. So, S 0 and S 1 is done. So, these are the states where in next state x 1 is going to be true, at least one path is there. So, such states will of course obviously hold the value of E x 1 until x 2, because from these two states at least one path is there where in future x 0 is true. Along with that, so in this case the S 0 and S 1 qualifies, but along with this condition we cannot take both the S 1 and S 2 now, sorry, S 0 and S 1 cannot be taken right away, even though both has a path where x 2 is true in the next structure. We have to ampersand it with the case where x 1 is true in the state, like this is the next. So, from S 2 pre we are directly going to get state x 0 and S 1. Now, you have to ampersand it with the cases where the state x 1 is true. So, we are going to have state where x 1 is equal to true, as well as the states from where in the next x 2 is going to be true. So, of course, you will find out that S 0 will get eliminated because x 1 is false over here, but we will retain S 1 because x 1 is true over here. So, now next one is something like this. Operation, applying operation dot on B of psi 1, psi 1 is nothing but x 1 and pre of this one is S 0 and S 1. So, this one is only satisfied by state S 1, because at state S 0 x 1 is false. So, you are going to apply this operation and we are going to get the BDD of S 1. So, the step 4 what it is going to return? Step 4 is going to return the states in which case x 1, that is psi 1 is equal to true, and there exists at least one path where in the next state x 2 is going to be true. So, that is what is being returned by S 1 and which is this BDD, represented by this BDD. Finally, we have to OR with, so finally we will get the answer S 1, which is satisfying the clause that in the present state x 1 is true and in the next state x 2 is true, that is phi 1 until phi 2. Next, basically we have to take all such states where x 2 or psi 2 is by default true, that is basically your OR operation of B of psi 2 and whatever we have got, B of psi 2 is the state where by default x 2 is true. So, that actually happens in state this one. We are going to get an OR operation on this, and finally, we are going to get the answer of BDD S 1 and S 2, which is this BDD. So, this is the answer of apply. So, now what we have got? So, in this iteration we have got S 1 and S 2. So, what is that? So, now in this iteration we have got S 1 by the virtue of the fact that here psi 1 is true and in the next state psi 2 is true. That is by this complex, by this part of the formula we have got this one. By this part of the formula we have got the solution of S 1. Now, we have to do this OR operation and this one will be done by this one S 2 is simply where x 2 is true. So, we are getting by this iteration we are getting the value of S 2 over here, that is just a simple operation. Finally, this is the BDD where EU psi 1 until psi 2 satisfies and with the answer is state S 1 and S 2. Now, there is a story. Intuitively we have seen that S 1 and S 2 suffices, but algorithmically no, because algorithmically you have to stop only when there is no change, there is a fixed point or all the states has been taken into picture. So, now in this case initially you had stored, if you look at B of psi is all the states of the system, right. So, now initially what we have done, B of psi 2, if you see we had what, B of psi 2 in this case was S 2, right. So, now we had stored x 2 over here and now sorry S 2 over here, because initial psi 2 was S 2. So, we have stored S2 over here. Then we have updated this. So, what we have got it over here? Here we have updated and we have got here was S1 and S2. Okay, now we have to repeat this until these two are equal or not. So, in this case they are not equal. So, there will be another more iteration. So, now again in the next state what is going to happen? We are again, this one is psi 2, x was only S2 in the initial round. In the second round you are going to change this one and you are going to you are going to replace S1, this one with S1 comma S2 and again rerun the whole algorithm again to see what it returns. So, now your Bx is having the value of S1, S2. Initially it was only S2, but now B of psi 2 has been changed. It is now S1 and S2. So, Bx in the next iteration become S1 and S2 and we again redo the second iteration. So, let us see what is the second iteration. Yeah. So, this is iteration 1 is done. So, this is iteration 2. So, only change is now psi 2 has become S1 and S2. It was just similar. So, if you look at, so again in this case only your psi 2 has changed because now it is S1 and S2. In the initial round it was S2, but x1 is anyway changed. So, you will first do again the same step, calculate the pre of psi 2. So, in this case it will be states S0 and S1, just you can do the computation. Then again we will go for the application of dot operation on B of psi 1 and this one we will get the value S1. You can just do the check and then again apply operation of B of psi 2. Psi 2 is this case states where default the formula is true and OBDD of S1 which you have got in the last step and then finally we are going to get the answer S1 and S2. Just the same states which I have applied in the round 1 and I have shown you in details. Same thing you have to just apply with the change of psi 2 of S1. Psi 2 is now becoming S1 and S2. Same 4 steps, 5 steps you have to apply. Again finally you are going to find out that I am going to have the answer of S1 and S2 again. So, now initial round we had psi 2 equal to S2. After doing it answer was psi 1 and psi 2, sorry x1 and S1 and S2. So, you have to again iterate. But in the second iteration you will find the answer is equal to S1 and S2. So, at this iteration you have to stop because there is no further addition and we have reached a fixed point. That is again I am going to come to that algorithm. So, now we started with S1 and S2. After completing this iteration again the answer is S1 and S2. There is no new more states has been added. So, you have to stop the iteration. First round we had B of x equal to only S1 and we added one more state that is S2 in that round and in the first iteration. So, we again go for second iteration to check if any more new state can come. But we finally concluded that no more new state has come. So, only S1 and S2 is going to satisfy the formula, fixed point is reached and you stop over here. So, intuitively also we had seen that only in the case of S1 and S2 there exists a path where in future x1 until x2 will satisfy because in S0 this is false because x1 is not holding, even x2 is not holding. So, intuitively S2 will not be a part of the state set where the formula will be satisfied. So, similar things again I have got it with the help of this symbolic model checking. I am getting the answer S1 and S2 over here. Just you can repeat the calculation and we are done. So, basically we have seen how the 3 important or the 3 basic formulas required to replace any CTL formulas like EX, EU and AF can be handled symbolically. Now, given any very complex formula, you can just use these 3 basic formulas to represent them and you can do this model checking symbolically. So, what we have achieved? So, we have seen that model checking is a very powerful tool which can automatically tell you which of the states which are satisfying the formula. If some states are not satisfying the formula or if any of the states are not satisfying the formula, why it is not satisfying the formula, some counter examples are also generated. So, you can mathematically you can prove whether your system is going to satisfy the requirements you want to design. That is the beauty of model checking. But problem with explicit state space modeling is the exponential complexity. So, to handle very large scale systems or complex systems, we have to go for symbolic model checking. That is, you have to model them using BDDs without explicit states modeling and the labeling or model checking can be done as we have explained in the 2 lecture series of 4 and 5. But again, this as you are going by BDDs, as already I mentioned several times that higher level decision diagrams, HLDDs, mathematical decision diagram, arithmetic decision diagrams, still people are working to find out how they can be used for symbolic model checking. BDDs are widely used for symbolic model checking, but if your systems are if you want to model them in an abstract level by using our register transfer level models or arithmetic decision diagram levels, still model checking algorithm in those level of BDDs does not exist or under research. So that is a very open and interesting problem to research upon. So even as we are telling in the course that we are handling NOCs and SOCs, but symbolic model checking directly, if you want to say that I want to use a very large NOC to handle it, it is not directly appropriate as of now to do it in that quote unquote fashion that I can use symbolic model checking to model a whole NOC. That is quote unquote not as simple as to do, because BDDs also has a limitation. To handle NOC and SOCs, as we have already seen in the testing part and several other parts, that we can use a high level decision diagram to do that. So again, if you want to have a very nice optimization answer, you should have a symbolic model checking at the level of arithmetic decision diagrams or high level decision diagram, which is not, unfortunately, which is still under research and not as matured as your symbolic model checking using BDDs. So that is where I want to conclude this 2 lecture series on symbolic model checking, and next we are just going to see something called a bounded model checking. That is, in future we do not want to extend the future to infinity, because in a practical sense future is limited. So maybe we will just explore up to a few state iteration and try to conclude something and get some optimization out of the solution. Symbolic model checking does not hamper any of the quality of solution. It just represents states as a symbolic BDD manner and does the computation for you. But on the other hand, if you are using a bounded model checking, that means you are not allowing to full extent to check. Future means maybe 10 iterations, 20 iterations, 100 iterations. Future cannot be infinite. You put a bound on that. So in a very layman's language, it will have slight impact on your situation or your verification answer. Maybe something would have been failing after 10,000 states, but you are checking only up to a certain limit. So but in a very large scale system, that is what is the optimization solution. So in the next lecture on verification, we are going to discuss elaborately on your symbolic model checking. Thank you.